Welcome. Uh, This lesson is about finite different methods. So you will understand the finite difference method for solving differential equations. Let me just tell you uh, uh, why do you need to learn finite difference? Because you might say, oh, why do I need to learn this? I could already uh, use a code that's out there that is already doing this for me, and I don't need to learn how these codes work. I need to learn how to use these codes. For example, ModFlow, ModFlow, for example, 2005. This is built on finite difference method. Other code, for example, like phi flow, that is built. So this is finite difference, or like sutra. These are built on finite element. Other codes could be built on finite volume. Yeah. Typically, you will just use these codes that will have this for you. So let me just give you an example. So like you have an equation, let's say delta square delta h over delta x square is equal to over k. So you have like this equation. What mod flow or phi flow or sutra, it will solve this equation for you numerically. Yeah. But there is, as I showed you, for example, in when we are doing like PFAS modeling, the guy come up with a mathematical model like this, and he didn't solve it with MudFlow or FeeFlow or Sutra or any of the like above the shelf code that you can get, because he had a new mathematical model that like these codes cannot do for cannot like solve him. Yeah, like this code only have like whatever equations they have, but they don't have this new mathematical model. And in my career, for example, I know sometimes one time, for example, like or several times I use MudFlow, one time I use Sutra. I also was involved with FeeFlow, but other times I had a mathematical model like this, and I just solve it on my own with MATLAB or finite differential equation solver. So I had this twice once, for example, when I was modeling a patch experiment for absorption, and another time I was modeling air bubble, and how like so you have like in the saturated zone you could have air bubble, and how this air bubble you can have like your contaminant could go inside this air bubble and go outside of it. So that for a model like this, this is MudFlow, for example, or FeeFlow or Sutra does not have these types of things. So I had to, in that case, I didn't even develop like use the finite, the differential equation solver of MATLAB. I actually had my own numerical method, and I solved this numerical method by myself. So there are like three levels. Like the first level is that like you use an existing code, ModFlow. Yeah. And ModFlow will have this equation, it will have a structure for your input, your output, and so on. Like so that's like off-the-shelf code, for example. ModFlow is just an example, like off-the-shelf code, like an existing code or model, existing code or model. The second level is that you come up with your own equation and there's no existing code or model, and then you use like a solver, like ODE or PDP, partial differential equation solver of like MATLAB, for example, or Python. The third level is that you don't even use like a solver, but you just solve the equation yourself, as I will show you in this lesson. Like I will show you in this lesson like how you can have an equation that looks something like this, for example, how you can get like a numerical version of it, and how could you solve it not using like an existing solver like a MATLAB or Python, but how can you solve it yourself? Okay, like using finite difference method. Yeah. So how can you solve it yourself? That's third level. Like, why are we learning this? Because it is important to know not just to use these codes, but to learn how they work. Uh, so, for example, when you're reading the manual of FeeFlow, for example, or Sutra, or FeeFlow or MudFlow, you will understand what they're talking about when you see, like, okay, this is the government equation and this is how we numerically solve it. So basically, the numerical solutions that I showed you here, this is from the MudFlow manual. Yeah, so it is important to so you be able to learn to be able to read the manual and understand it, but also in case, just like myself, where you have to come up with your own mathematical model, and this mathematical model, just like the PFAS models that I showed you, for example, the PFAS model, it does not have an, there's no off-the-shelf models that you can use it, and you need either to use an existing solver or even come up with your own numerical method and solve your own numerical method on your own. Yeah. So that's basically the idea. Like, why are we learning this? I don't know if you understand much of what I'm saying now, especially if you don't have like a previous modeling experience, but that's fine. Hopefully, by the end of this lesson, you will understand something. I mean, if you don't understand everything fully, that's fine. Don't worry. I understand that this might be like advanced. It's not advanced topic actually. It is kind of uh, yes, this is big part actually of this course. Like if you read the catalog course description, big part of it is around these things like numerical solutions and of ordinary differential and part of like differential equations. So that's actually a big part of your course. So I tried my best to simplify it as much as I can and be very basic. Yeah. So let's just start by an example. So here is an example. Like here I have a model. For example, let's assume this is a model and I want to simulate flow, like the hydraulic head here. And I have head here, for example, let's say with a value, and I have head here with another value, and the initial head is constant. So head at the left is equal to head at the right. So that's like H0, yeah, it's constant. Let's assume it's just constant. Now assume that like the head at the left just dropped. So instead of being, let's say this is 10, it dropped to like 3, yeah. So my question to you, what will happen to this head? So here head is constant at time step 0. If the head here drop, what will happen here? So obviously the head here would be 3, and here it will be slightly like larger than 3, and here it will be like at 10 or whatever. But this is just at the first time step. So let's say after 1 hour. After 2 hours, what will happen? Here it will remain 3, here it will remain 10, but here it will be something in between like this maybe. That's like after 2 hours. Yeah. After 3 hours, it might like reach a steady state, and then you will find like a head. So here it will be 10, here it will be like 8, here it will be like maybe 5, here it will be 6, and here it will be like 3, something like this. Okay. So basically that is how the system, so now you see the system is not only evolving in space like in y, so this is like your y direction, but it is also evolving in time. So the head is not only changing in space, the head is changing in time. And can we describe this? Yes, we have differential equations that can describe this with this boundary condition. So here I'm showing you how head is changing in time. Here from one time here to another time here to a third time here, but also it describes how the head is changing in space. So you see here, 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 here at a given time step. Okay. And we are describing some boundary conditions. So here we have a constant head boundary condition, or like uh, at the left hand side, this is the type 1 boundary condition, Dirichlet boundary condition, and we have an initial condition. So at time 0, the head was constant, whatever that value is. And now, so this is our mathematical model. So how can we solve this numerically? So I didn't show you like the previous analytical solution. It was not for this case. It was for the case where at steady state, like that was equal to 0. But now for this case, the analytical solution might not be available, especially if it is heterogeneous. We have to solve it numerically. Yeah. And to solve it numerically, the first step you do is that, like, this is your model. You basically discretize your model into cells. Yeah. Because now we will be calculating the head in each of these cells. That's how the numerical solution work. So here, so this is our model. We discretize this into cell. I'm getting this from the MudFlow manual. So here, that is like your first cell, like your second cell, third, fourth, and fifth. And here, that would be like this would be your boundary. So this would be like your head at the left. That would be your head at the right. Yeah. Uh, Here, this would be like your delta y, delta y, delta y. Okay, so each of these is delta y. Here, that is like your delta x, which is like you can just assume it's equal to 1. And this is your b, like your delta z. Yeah, this is your delta z, which is equal to b. So basically, you discretize your model into cell, and the objective is we want to, so we know the head here, this is given, we know the head here. Can we find the head here? Can we find the head here? Can we find the head here? Not only as a function of space, like in y, but also as a function of time, like at different time steps? Yes, we can do this. So, but first step is that we discretize our model into grid cells. And then we similarly, so here, this is an example. So you can do this discretization in a different way. One way is called like mesh centered, and one way is called block centered. So mesh centered is means that I will calculate the head at, so this is my grid cell, and I will calculate the head here, here, and here. And so this is mesh centered. Block centered means I will just calculate like the head here. So let's say like here is 110, here is 100. So let's assume this is 101. This is like here is 101. So the value here, for example, the head here would be 100.5. Yeah. And then I calculate the head here and the head here. So MudFlow, for example, it uses a block center scheme. So it uses a block center scheme. So if I use a block center scheme, how many columns will I have? Or how many cells? Like, so I will have here, like, this is delta y. Here is my delta y. Here's my delta y. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So here, like the mesh center, it has like, if it is mesh centered, like this is mesh center, it will have 11 column. If it's block center, it will have 10 column. Yeah, MudFlow use a block center. Okay, for example. So here is an example. This is from my MudFlow manual again. So you see here is this, you discretize your domain. So that's your domain, that's your modeling domain, and you discretize it into, like, so this model, for example, has 5 layers. It has 5 cell in the X direction or the Y direction. It has 9 cell in the J direction. And basically, you will be estimating the head here, 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 like block centered. Yeah, in each of these blocks, you will be estimating the head. Yeah, and this would be, for example, like that would be your delta y. Here, that would be like your delta x. Sorry, that would be your delta z, and that would be here your delta x. Yeah. So each cell has a delta x, delta y, and delta z. And they can be different. They don't need to be similar. So they could be, so here delta z here could be different than here's and here's and here's and here's. They don't necessarily be the same. Same and in the y direction. and same in the x directions. They don't need to be similarly. So as you discretize your space, but you also as you discretize your space, you also discretize your time. Yeah. So and we have seen in the previous example, that parachutist example, I showed you like how to discretize your time, and with the final time discretization, your numerical solution, for example, would be more accurate and will approach the analytical solution. Yeah, the exact analytical solution. So for example, like I showed you, like in this parachutist example, I showed you delta t is equal to 2 seconds, and like another delta t is equal 0.2 seconds. And again, like this doesn't need to be constant. Like for example, like if we look at the parachutist example, we had something like this. Maybe at the initial time step, when you have this big jump in velocity, in this initial time step, you can consider very small delta t, like you can say like delta t here is equal to 0.2, 0.2, 0.2, like all this here. And then once you get here, you can make delta t is equal to 2 seconds. Yeah. So delta t does not need to be constant. Yeah. It also could change. Just as delta x, y, z could be different along your in space, delta t could be also different in time. Yeah. But so now, so this is the first step. So let me repeat again. What's the first step? The first step is that you discretize your domain into x, y, z, and in time. Yeah, if it's a 3D model. Yeah, if it's a 2D model, that would be x, y only. Yeah. So here, this is just 1D model. So basically, you just this is a 1D model because we are it's 1D in space, yeah, and the time is like the second dimensional. So it's 1D model in space, and basically we just discretize this here. So this is my delta y, yeah, this is my delta y, my delta y, my delta y, my delta y, and I will assume that it's constant, yeah. So this is my delta y, yeah. And you can assume here this is like your delta x, which is equal to 1. Yeah. So how could I discretize, like how could I, like, so this is now a differential equation. How could I make it in ways that I can solve it numerically? Do you remember, like we did this in the previous example, in that parachutist example? So like a guy like this, for example, what you can do with him, you can say like this is equal to delta h over delta t. So you change this partial to this delta, to this approximation. Like, so this derivative where you find the exact slope, you just take the difference. Yeah. So an equation like this can basically be an equation like this can basically be uh, approximated as something like this. And you know where this came from, yeah? You know where these came from, because that is like partial h over partial t. That is approximately equal delta h over delta t. So delta h, that would be what? So that would be like h I, okay? Hi. So this is like here, I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, and I is equal to 5. Yeah. So delta I, yeah. Uh, so delta, that would be like t plus delta t. We did this before in the parachutist example. Negative delta I, and in the previous time step over delta t. Yeah, that's basically where this guy came from. How about this guy? Well, this guy you need, do you remember the meaning of this guy? Let me show you. So the meaning of this guy is here. So the second derivative means that you can express it like this, and then I can express this guy as a delta, and I can express this guy as a delta, and I can express this guy as a delta, and I can express this guy as a delta. So what does this mean? This means basically here, this is the difference of the difference. So this guy, remember, like this guy would be equal to what? So delta H over delta Y. So that would be, for example, delta H I plus 1 minus delta H I. Yeah, at n here. I will tell you what is n now, like why I didn't use T or delta T. Okay, so basically, like this is what this guy is. But here I have like this guy, like the difference of this guy. So basically, like what this means is that I have like the delta here is means that I have like delta H over delta Y, like 2 minus delta H over delta Y 1. Yeah, so that's basically this delta, what does this delta mean? Yeah, okay, and each of these guy is equal to this guy over delta Y. Yeah, so here, this guy, okay. And that's, so if you did this and you just follow like this derivations that I have here, so you can pause the video and look at this. I think that's easier than just listening to me. Just pause the video and see how from here, and try to drive it yourself. I think that's how you will learn it. Like, see how from here I was able to express it like this, and how this guy I was able to uh, simplify it uh, like this. Yeah, to express it like this. Except here I have this n here, so I could have like, I forgot to put the n here. So you have an n here, you have an n here, you have an n here. So what is this n? Yeah, so what is this n exactly? So this n basically tells you something about the time. So let me show you here what this equation means. So basically this equation means that this value, yeah, this value here, it does not depend on 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 this value here. Let me show you. But rather it does not depend on, like, so this value here, so that would be hi. Yeah, so that's like hi. This I in that case is equal to 2. Yeah, hi is equal to 2. It does not depend on hi plus 1, which is like 3, nor it does depend on hi minus 1. Rather, it depends on the difference between like these two guys and the difference between these two guys. That's exactly what it means. So it depends on like the difference between these two guys and the difference between these two guys. So my value here is not really controlled by like this value, but it's more controlled by the difference between these two values and the value and the difference between like these two values. That's exactly what I say here. And that's why this is like the difference of the difference, if that makes sense. Yeah. So if I arrange it like try, like I think like try to drive this and try to get to this equation, but like simple, like to put it in a simple term, like my value here depend on the difference between these two values and the difference between these two values, and that's why I have a second derivative. It is like the difference of the difference, like the difference of delta H over delta Y. So it's the difference of a difference. Yeah, okay. I don't know if this makes sense to you, but anyway, so you got like an equation, but that's all these details are not important. Like if you don't understand this, that's not important. Like what the main important thing that you should understand here is that, like, if I have equations that looks like this, I still didn't tell you what is n here. So n basically, let me just tell you what is n now. So like why this is not like you would expect this to be delta t or something like this, but why it is not like uh, t or t plus delta t? Because I can, this is, I can compute h here, yeah, and when I compute h here, I have to use the value of this guy and the value of this guy. So now should I use the new value or the value at my previous time step? So if I want to use the value at my previous time step, so n will be equal to t. If I want to use the new value at the new time step, in that case n will be equal to t plus delta t. That's the meaning of this n here. So let me show you here. So this is called like explicit difference, where I estimate like, so now here this is h at, I want to estimate at t plus delta t I. I will base this, I will not use, I will use the value of this guy and the value of this guy not at t plus delta t, but at just t, like the previous time step without delta t. This is called explicit difference. If I want to use this new value, then n will be t plus delta t, and that's called the implicit difference. This one, the explicit difference, it is simple to implement, but not only conditionally stable. Like, while implicit difference is more complicated, but unconditionally stable is like more stable. So let's for the now, I will just like for the rest of this exercise, I will just assume that I will use the implicit difference. So I will say like n is equal to t plus delta t. Yeah. So if I did this, and then I can like, so my equation, like I will replace n here with this guy, with this guy, with this guy. I can arrange my term, and then I will get an equation that looks like this. You can try it, like arrange these terms, like do this multiplication and bring this guy to this side and this guy to this side, then you'll get an equation that looks like this. Now this equation looks a little bit complicated, but I can simplify it, because I can just take all this guy here and call him alpha, and I can take all this guy here and call him beta. So if I call this guy alpha and this guy beta, then my equation could simplify to something like this. Yeah. So take time is equal to 0, so t is equal to 0. So that would be like just at time equal to 0, and then you can do it for time equal to 1, t is equal to 0, and take this is equal to alpha, then I get an equation that looks like this. Well, where this is my alpha and this is my beta. So what does this mean? So basically this means that I want to find like my head here at like this guy, that would be equal to, or like the head here at this guy and the head here at this guy. So this is head equal to 2. That would be for this point. For the next point, so for the next point, like I, so in that case, so this is at node 2, like I is equal to 2. At I equal to 3, what do I get? So here, let me just write it down. So at I equal to 3, so I will get here I plus 1. So that would be h over 4 delta h minus alpha. This alpha I is equal to 3. So that is like 3 delta h plus here I minus 1. So that is h delta t, and I minus 1. So I is equal to 2. That's 2 is equal to negative beta, and then h here t is equal to 0, so h to the 0, and then I to the power of 3. Yeah, sorry, this is, did I get this correct? Yeah, so that would be I to the power of 3. So if you look here, you get like this same equation here. Yeah, so that's like how you do this guy here. So you got this equation here, and then here you can do this for this guy here. So this guy here would be like this value and this value, like, so that would be I5 here, I3 here, and then I can find like this guy here. Yeah. So now I have, is this linear equation solvable? Which are the known and which are the unknown? Yes, these linear equations are solvable, because I have like 3 equation with 3 unknown. Like my 3 equation is like for each node, for like this node here, this node here, this node here, and my unknowns are like H2, H3, H4. H1 is giving because that's my boundary condition, so that's H boundary like left. H5 is giving, that's my boundary condition, that's H boundary right. Yeah. So that's giving, so these are the three unknown, and I can like solve this equation for this three variables. Yeah. So let's do an example. But before we do an example, let me just show you one thing, is that we can also check for a single cell, we can check the mass balance. Remember mass, like Q is equal to volume over delta T. So you can express big Q, remember big Q is equal to small q time area. So you can express this as an area. Q, if you remember, like small q, that is delta H over delta Y, for example. So time K, that's Q, the hydraulic conductivity. So I can express this as Q and the gradient, the hydraulic gradient, delta H over delta Y, time area. So what is the area? So my area, that would be like my delta X time my H here. Yeah, so that's like, that would be my delta X time my H here, which we call it like B, and time my delta T. Okay, so I can take like the B and the K, that will give me the transmissivity. Like again, this detail, like this is not a groundwater class, so these details are not important, but I just like in case you're wondering where this came from. So the thickness times the K, that will give you the transmissivity, and then delta x would be equal to 1, and delta t, whatever that is. And that would be the difference between the head into adjacent cells. Yeah, and that would be the width or like of the cell. So that's V in, similar for V out. Here like H1, H2, H3, and then the storage volume, you can do the same. So basically that is like your equation for the mass balance. So if you did this, you can actually solve this problem with Excel. Let me, I will just show you the solution, and then in another video I will solve it. Yeah. Let me just show you now like the solution, and in another video I will like solve it like step by step, so that you can see the step by step. So this is the 1D with Dirichlet boundary condition, and you see here at the initial, like that's exactly what we were discussing. So this, in this problem, you have the head here is like 8.2 at the beginning of your model, and the head at the end of your model is 3.6. Yeah. So at the first time step, that's how the head will look like. Okay. It would be, so this guy would be more close to this guy, and this guy would be like, you will see some drop here. In the second time step, you will see more drop. In the third time step, you will see more drop. And once you reach a steady state, you will just get like this uniform distribution of head, just a straight line, basically. So the solution, like, the solution of this equation in a steady state is just a straight line. Yeah, it's a linear. Yeah, but at different time steps, that's like how the head will vary. I will show you in another video, like I will calculate this with you like step by step, so you will see, for example, how to, like if you have an equation like this, how to apply it numerically to find head here, head here, head here at different time steps. But this is an optional video, like you don't need to know this. This is just an optional video for the student who want to learn more. But for most student, basically like the most important thing is not like these solutions. The most important thing is the basic concept. So the basic concepts, let me review the basic concept. So the basic concept is I have a mathematical model that is something like this. Yeah. Now this mathematical model, I can solve it numerically by making a grid and expressing my equation in a form that can be solved numerically. And then once I express my equation in a form that could be solved numerically, I could either solve it numerically by myself, as I will show you now is Excel, or use like an existing solver, like an existing MATLAB solver or Python solver or whatever. Yeah. Uh, so I will show you like in another video like how to do this. But anyway, so that is basically how you can solve like an equation like this numerically. I know it's a little bit tedious, it might be a little bit advanced, but that's okay. So here, this is like your homework question, finite different equations. We have these equations here with alpha and beta. So take time 0 at node 2 and 3. You have like this guy and this guy and this guy. So this system of linear equation is non-solvable. Is it non-solvable? Is solvable for unknowns H2, H3, and H4. Yeah, H2, H3, and H4 as H1 and H5 are boundary value. Yes, this is the correct answer. So this is wrong. This is the correct answer. Is solvable for unknown 2, 3, and 5, like 2, 3, and 5, with this as a boundary value. This is wrong because this is also a boundary value and this is a boundary value, so this is wrong. Solvable for unknown 1, 2, 3, and 4, and this is a boundary value. Also, this is wrong because both these are boundary values. So the correct answer here is B. Okay. Let me show you another case. Remember, like there are different types of boundary conditions. So I showed you this for type 1 boundary condition. But what if you have a flux boundary condition? So if you have a flux boundary condition, what you do, like the solution technique is generally you assume like an imaginary boundary here. So basically, like in the mesh center, you assume an imaginary boundary here, and then you find your delta H over delta X, like the flux from between like these two nodes, like this node and this node. And that's basically how you calculate your flux, and that your boundary condition will take this form. So that's just for your information. Again, like the details are not important, but I just wanted to show you this for another type of boundary condition. So again, this is the same exercise that I showed you here for this exercise here for the type 1 boundary condition. I'm also providing the Excel sheet to see it in with if you want to solve this with a no-flow boundary condition like type 2 boundary condition. So I'm also showing, like I'm providing the Excel sheet. In a separate video, it's optional to watch. I will show you basically step by step, like how to find like the head here, the head here, the head here, how to calculate, like check your mass balance, like volume in, volume out, and check change in storage, and how you can calculate this for like different time steps and then plot it. Like, so here, this is the plot for time step 1, this is for time step 2, and this is for time step, this when you reach is like a state of equilibrium, because you see here this is 8, 7. See, like starting from here you started to reach equilibrium, like the values is not changing really much. Yeah. Okay, so that's all for this lesson, and I will see you in the next video.